Hello, physical geology students. Tonight we're going to talk about volcanology, or just volcanoes. We're going to talk about volcanoes, molten rock, and how molten rock leads to volcanoes having certain characters, and then the hazards that we associate with volcanoes as well. So, all of this, of course, I think is something that most of us are familiar with, and on some level, not necessarily because we've lived through a volcanic eruption. We certainly heard about them in the news. They occur, of course, infrequently, generally, unless you're in Hawaii and you're talking about a volcano like Kilauea, which was erupting for a very long time last year, pretty well continually for a while. Most volcanoes are erupting once, once in a great while. Mount St. Helens or a volcano like that. So, and we can't really predict when they're going to erupt. We have some data that gives us some idea when they're going to erupt. We can't predict it. So, all right, let's talk a little bit about some of the basic stuff that you're all familiar with. Of course, most likely, you're all familiar with magma and lava. We've heard those terms before, anyway. Magma is, of course, what we call molten rock when it's below the surface. Lava is the name we give it when it's on the surface or outside of the earth. So magma is an intrusive term, lava is an extrusive term. Lava, once it exudes onto the surface, can come in a couple of varieties, pahoehoe and aa. Pahoehoe are the ribbon-like lavas that you see over here in this image, and aa flows are much blockier and they don't move nearly as fast. Both these are Hawaiian terms. So the cooling of lava or magma is actually the freezing of lava or magma. And it can be rapid or slow. And if it's really rapid, the minerals that crystallize from that lava and magma are going to be small. If it's slow, they're going to be bigger. And we'll come back to that the next chapter when we talk about igneous rocks, because that has significant bearing on the kind of rocks that you get from volcanic activity. So Kilauea last year was erupting quite a bit, and here's an image of some lava heading down the highway. Kilauea is one of a number of volcanoes in Hawaii, and of course, Hawaii being a hotspot, as has already been discussed, hotspots, of course, are stationary plumes of mantle material that make their way up to the Earth's surface, and then make their way out as generally will pool under the earth, under the crust, and eventually will come out as through vents. And these are typically shield volcanoes, and so Hawaii, the Bay Island of Hawaii, has several active shield volcanoes. Kilauea is just one. Here's some images. A typical shield volcano eruption on Hawaii, where these nice fire fountains, and obviously these are still dangerous and quite hot, but you can walk relatively close to them. Here's some more. Here's, of course, it's burning through a forested area. This is closer to an aa flow. Not quite there yet, but it's closer to that. It's a little block here. But here again, it's running down the road. But this is just taken from the eruptions last year. Leilani Estates, I think is how you say the neighborhood that was largely destroyed by or significantly damaged by the eruption. Here's an example, of course, of how lava can be a hazard. Now, you can outrun this lava. Generally, now this particular flow you can. Some of the flows that came out of Kilauea last year were quite rapid, especially right out of the vent. You would not have been able to outrun those. So this the area that was mainly affected by lava flows, of course, are in red here, and especially Leilani Estates, this region in here, all along the East Rift zone of the island. But Hawaii is not alone. Hawaii, around the Pacific Rim, looking specifically at volcanoes that are in the United States, but so I'm not including anything beyond that. So we have here Kilauea in Hawaii, and then we have some of the volcanoes associated with the Pacific Islands that are territories we own or we administer. And you can see here that the Aleutian Islands and southern Alaska are quite active volcanically, as is the west coast of the U.S. Now, of course, we know that Hawaii is a hotspot. These are not hotspot volcanoes, nor are these. These are the result of subduction zones. So that's what you got going on here, right? So you've got some volcanoes that are associated with spreading centers, divergent boundaries, an Iceland situation, or any mid-ocean ridge, really. Oops, get ahead of it there. And then other volcanoes that are associated with hotspots. And then still other volcanoes. These are generally the more complex chemically, that are associated with partial melting of the upper mantle, not the subducting slab, partial melt of the upper mantle and associated sediments and so forth. Water is brought down, and so these materials are hydrated, which actually lowers their melting point and causes and allows for the magma to rise. But you're generally going to get an arc of volcanoes along a convergent boundary like this. Whether it's oceanic to oceanic convergence or oceanic to continental convergence, you're generally going to get some volcanoes. So again, island arc plate subduction, you'll get volcanism. Divergent plate boundaries, you'll get volcanism. Hotspots, of course, you get volcanism. And then continental plate subduction, you still get volcanism. So anywhere you have a plate boundary, you're going to get volcanoes, just like you're going to get earthquakes. Again, volcanoes and earthquakes are two of Earth's ways of releasing energy. That energy, of course, emanating from its interior. And that plate tectonics as a whole is the process of energy release through the various moving around of plates on their boundaries, but around their boundaries and so forth. But these peripheries, these boundaries are important. The features are the volcanoes and the earthquakes that help release. So, of course, these volcanoes are not limited to the regions I was just pointing out to you. Volcanoes are all over the place, and just like earthquakes, they occur just about everywhere else in the world. So, obviously, Southeast Asia has quite an array of volcanoes, but as does the Mediterranean and into some places in the Middle East. The volcanoes may be of a slightly different character, but they're still volcanoes nonetheless. Now, a word briefly about the geothermal gradient. In order to melt rock, you have to give it heat, or there's a heat and pressure situation. So you need to increase the pressure and the heat until the geotherm, which is the red line in each of these images, crosses the green line. So below this green line, everything stays solid. Above this green line, you get liquids. So we look at the mid-ocean ridge, where there's a lot of heat at a relatively shallow depth. You don't get, I said temperature and pressure. Yeah, this is pressure over here. This is temperature over here. So you don't get a lot of, you get really high temperatures, but not really high pressures generally. So you can cross the solidus, and you're also getting water as well. You can cross the solidus and get melting. Now, over here at the hotspot, the same thing happens, except that it happens at a deeper deeper level within the lithosphere. Now, here you have a situation where you have with the island arc volcanism, or you could say it was continental arc volcanism, same thing, because the reason things are melting here is because the solidus has moved, and the solidus has moved because you're bringing water, you're hydrating this part of the upper mantle and the lithosphere. Upper mantle is part of the lithosphere. You're hydrating this part of the lithosphere, and that lowers the melting point of the rock, and so the solidus moves. So the geotherm is not really any different than the geotherm in a normal situation, but you've added water, and that does make a difference. And of course, so depending on the water content of the lava or the magma and the silica content of the magma, you'll get different kinds or different characters of eruption. So when you have the silica content that's high, around 70%, you'll get your most explosive eruptions. Those are also the kind that have the most water and highest gas content, particularly water. Sorry, it's a little late tonight. The basaltic lavas tend to be around 50% silica or so and have much less gas content. So you can see it's not a perfect, you don't just move into one and move into the other, but you can have cinder cones and you can have uh, dome complexes at the same time. Likewise, you can have cinder cones and composite volcanoes and shield volcanoes all existing concurrently. But generally, they exist because of the character of the lava. And you can see that lava flows occur mostly with shield volcanoes and cinder cones, and much less so with composite and so forth. Lava domes and pyroclastic deposits. These are the messy volcanoes with the ashy volcanoes, and these are the lava-rich volcanoes down here. So the silica content's important because the higher the silica, the more viscous it is. Over here, this is less viscous, and so that makes a difference with the magma. So here's a summary. You can pause here at this particular slide to sort of study it for a while. That gives you a summary of the different eruptive products that you can get from a volcano, including the pyroclastics. And of course, magmas themselves, and we'll talk more about this next week when we talk about igneous rocks, but magmas themselves are not compositionally homogeneous. They can be very heterogeneous. They can just have pockets of various kinds of magmas within the larger magma body. You can have a magma chamber can be stratified like this. Of course, magma chambers aren't necessarily, probably usually aren't big open spaces within the earth. These magma chambers here are what you would see here, of course, these plumes. And you can see there's a lot of mixing going on within that magma chamber. There's going to be some convection going on, and magmas from different chemistries are going to mix. And so you can imagine as this cools, the rocks that are produced and the mineral assemblages in those rocks will be very useful for telling us something about what the history of that magma chamber was. So briefly, just to illustrate the differences in geochemistry, here's a TAS diagram, and this data is pulled off of the EarthChem portal, which is free. We'll check it out in lab, but we're just comparing sodium and potassium by weight percent to silica. So, this is Kilauea, so it's mafic. It should have low silica content. And indeed, it does. It's got low silica content down there, around 48, even down to 40% silica content. You can see there are some samples that have been collected from Kilauea that are richer in silica, but generally they cluster way down here. If we move over to Yellowstone, I only have a few samples here. You'll notice they're mostly rhyolite. So Yellowstone is continental, which means that the continental crust, lithosphere, which is granite primarily, is going to have a significant effect on the chemistry of the magma. And then you look at Mount St. Helens, and it runs the whole gamut. So it's not very mafic; it's more andesitic, but you do have a significant rhyolite component. So Mount St. Helens is going to be a very explosive eruptor when it erupts. Vesuvius. Now check out how things have changed here. From basalt to almost purely rhyolite to a good mix to so intermediate andesitic. Then suddenly the chemistry goes wacko, and you end up with so much potassium and sodium. The weight percents haven't changed that much, but a lot more sodium and potassium together were the Italian volcano of Vesuvius. So, you could identify a volcano ostensibly from its chemical signature. Okay. Let's talk about shield volcanoes. Shield volcanoes, as one of our big types of volcanoes, generally are very large volcanoes in terms of aerial extent. Not necessarily super tall, although the tallest mountain on Earth technically is a shield volcano. It's Hawaiian. which I might be getting this wrong. It's just I mentioned at the top of my head. I'm pretty sure it's Mauna Kea, or Mauna Loa. I'm pretty sure it's Mauna Kea. Anyway, they tend to be thin, but very, very, very broad, and with very gentle slopes. So here's some examples. There's I'm pretty sure this is Mauna Loa in the background, and this taken from Mauna Kea. And here's Kilauea, another shield volcano. Here's a picture of Mount Suswa, which is in the East African Rift Valley, a beautiful shield volcano. I was there last year, I should say the early January of 2018, and was able to go and walk in the lava tubes. And they are pure basalt and obsidian, lovely, lovely to behold. Stratovolcanoes, by contrast, are very steep. This is the image taken straight out of the textbook. So if you're curious about the numbers, you can go to the image and the textbook and click on them, and it tells you all about them. But these volcanoes tend to have very steep sides. This is a bit of an exaggeration, but you get the idea. But the big thing is that they're a composite of alternating layers of lava and ash. And so they also have the name composite volcanoes. Here's an example of one. You can see the steeper sides. Here's Mount St. Helens blowing its top in 1980, erupting sideways. Here's Mount St. Helens again, showing you there where the current summit is and where the old summit used to be. Okay, this volcano is near and dear to my heart. It's when my wife and I first met. This is Santorini. And of course, if you go to Santorini, it looks like this. It's just beautiful, bucolic landscape. But right over here is these cliffs are the part of the volcano. Right? So this is Nea Kameni, the island in the center. And then these are all cliffs around the interior. So when you visit Santorini, you go in a boat, and then you head to the town of Fira, where you disembark and go from there. All right, cinder cones and volcanic fields are often the ones that are less discussed. Volcanic fields and cinder cones, where you have anywhere where magma is pooling underneath the lithosphere, you can get cinder cones or a volcanic field. Cinder cones don't tend to be as tall as stratovolcanoes, but they can still be very explosive in their eruptive style. Here's a cinder cone. It says this is part of the Mount Lawson area. I may be wrong about that. Calderas are another important type of volcano. Yellowstone is, of course, the type of caldera that everybody thinks about, understandably. But you can see it takes up quite a large bit of space. So caldera eruptions are potentially very dangerous eruptions. This is a schematic of what it may look like beneath Yellowstone on some level, or at least with an idealized sketch of what it might look like. You can see the Horst and Graben structure created by the volcanism. Here's just another image of Yellowstone National Park, but here you can get an idea of how big the magma reservoir is. So when you're at the park and you're checking out the hot springs over here in the center, you're literally standing on top of a huge reservoir of magma. So this is where you're walking around up there. Here's your plume of mantle plume, shoving up underneath the crust, the lithosphere rather, and some of that eventually makes its way up through the lithosphere, and eventually refills the magma chamber for Yellowstone, and eventually it will erupt. But it hasn't been in the same place its entire existence. Yellowstone is a hotspot, of course, despite its rhyolitic nature. And 16.1 million years ago, it was down here. And it's been moving to the northeast ever since. Another one is Toba. Lake Toba is another caldera eruption. Really massive eruption. It goes back, I forget exactly what the year was, but there were only 10 people left, and that was 10,000 people roughly around the world, which isn't much. This is in Indonesia. Here's another view of it. All right, volcanoes as a hazard have brought extinction. This little chart over here is an attempt to associate extinction with large volcanic events, generally large igneous provinces or lips. And this is in here just for fun, because couldn't you imagine a planet like the Earth once was, just filled with molten rock? Okay, so oh yeah, flood basalts. These are different flood basalt provinces around the world. Flood basalts are basalts that come out as a very broad sense, very floody, and have been associated with the Permo-Triassic extinction and the Cretaceous extinction, the ones in India. And so it's they're pretty important. We just haven't seen, no modern humans have seen one erupt. Here's some of the Columbia River flood basalts. You can see the layers of basalts and so forth. But this is what happened when they erupted this. They covered an area that large. It's a lot of area. Now in India, they have what it's called the Deccan Traps, and the eruption of these was associated with the end of the Cretaceous period and the killing of the dinosaurs, at least in part. Then there's the Deccan Traps. This isn't a very good image, but again, you can see the alternating layers of lava rock. And the Siberian Traps, these being associated with the Permo-Triassic extinction, are certainly large enough. Whether you have enough organisms and animals up there to make it work, I don't know. All right, these are also known as large igneous provinces. So there's mafic and silicic lips. You can see where some of these are located around the world. All right, bring it back home. Volcanoes in Virginia. We have volcanoes in several places in Virginia, as well as igneous intrusions. You'll look at one of them, the VFEs, one of the intrusions that I personally imaged in Highland County. The one everybody knows about is Mole Hill. Mole Hill is, of course, about 35 million years old and hasn't erupted since. It's just to the west of Harrisonburg. There are some others, Trimble Knob and some others in Highland County, and then a few dike swarms in Franklin County and Augusta County. This is a picture of columnar basalt on the Limberlost Trail, Shenandoah National Park, and this is a picture of what Mole Hill looks like today. So you can go up there if you get the permissions you need. Go up there and collect rocks and see all kinds of. You can see outcrops of basalt and so forth, but you have to get permission to go up there. Now hazards. These are important. But these are everybody's favorite things. So you've probably heard of these before, most of them. So let's go through them. And I'll use the context of June 3rd, 2018. Of course, there was this was June of 2018 in Guatemala. There was the Volcan de Fuego erupted and caused lots and lots of problems. And you can see where it is in the map of Guatemala there. Of course, that volcano released a whole lot of different kinds of hazards, including ash falls and pyroclastic flows, lahars or mud flows, bombs, lava, and so forth. But here are some fumaroles. So these are gas vents coming out of that volcano. And I won't show you the video now, but you can go look on your own. This is a video of a car driving away from Mount Unzen in Japan when it was erupting. That's a pyroclastic flow, superheated gas and dust. And of course, lahars. That's a bridge over there. Everything's caked in mud here. Here's another example in the Philippines from Pinatubo. That's the roof of the church in that particular area. So there's a lot of mud there. Other hazards include bombs and ash. You can see how big these bombs can be bigger than this or smaller than this. And of course, ash is a lot like snow, except you really don't want to breathe it. Now, one of everybody's favorite volcanoes is Vesuvius because of what happened to Pompeii. And you can see here, this is actually the lava flow that covered Herculaneum on the other side of the mountain. They had to excavate all of that away because Herculaneum was buried by lava. Pompeii was buried by ash and pyroclastic flows. There's a picture of Herculaneum as it is today. And again, this video is a really nice dramatization of what it might have been like that last fateful day in Pompeii. But again, volcanoes aren't just for Earthlings. This is Neptune's moon Triton, which actually exudes gas or water vapor as a gas and essentially acts like a volcano. And again, of course, there's a volcano on Venus, there's a volcano erupting on Io, and then Olympus Mons. And that brings us to the end of this presentation. Hope you enjoyed it. I apologize for being a little on the tired side. Let me know if you have any questions.